Hello everyone, and welcome to a single example using quantitative energy bar graphs. So we're now going to add in all of our numbers since we have now defined all of our math models for all of our different energy storage mechanisms and energy transfer mechanisms. So here is today's example. We've got the classic roller coaster. The roller coaster starts with a hill that's 100 meters tall. It starts from rest at the top of the hill, which isn't really realistic. I mean, you have to be moving to get over the hill, but we're trying to keep things simple. The mass of the car is 110 kilograms. It's a frictionless track, if you notice down here, which is nice because that means we don't have to worry about dissipated energy. And the second hill, which comes in part B, is 25 meters high. So, first thing we've got to do from an energy standpoint is to define our system. I want to put the car, the track, and the earth in the system. All of this. If I do that, is the system isolated? Well, the forces that would act on the car would be gravity, car and the earth, a normal force, car and the track. There's no friction, but even if there was, that would be between the car and the track. And we're neglecting air resistance, so all of the forces are internal. And therefore, the total amount of energy is conserved. So, here is our energy bar graph, our LOL diagram, if you will. We're going to start initially and then move to the energy flow diagram and then do the final, and then we will answer the question. So initially, at the top of the hill, there is no kinetic energy because it's at rest. There is gravitational potential, as I assume we would call point A 0. How much? Well, we can calculate that now. Let's say there's 4 boxes, but let's actually calculate that by using the EG math model. So the initial EGI, is mass times gravitational field strength times initial height, or vertical position. If we look back at the problem, we can see that the mass is 110 kilograms. Gravitational field strength, assuming this is on Earth, is of course 9.8 newtons per kilogram. And the initial height of the first hill, 100 meters. Multiply those 3 things together. Notice that the kilograms cancel, leaving us with newton meters, or joules. And we get 107,800 joules. So to make the energy bar graph quantitative, I put the top line as 107,800 joules. Now, energy flow diagram, there's our system. What's in our system? The track, the earth, and the car. But it's an isolated system, and therefore no work is done. And so really that's it for the energy flow diagram. Nothing is flowing in or out of the system. So finally, no E-dis, because after all, there is no friction. No EE, no elastic potential energy, no springs or anything. You're now down at the ground level, which is what we would call the 0 of EG, which means all of the energy, all 107,800 joules, must be stored as EK. So now we actually know, even without making any calculation, just by employing the law of conservation of energy, that if there's 107,800 joules of EG initially, there must be 107,800 joules of EK finally. And since our EK math model is 1/2 mass times speed squared, we can solve for the speed and answer the question. So to solve for V, first thing we're going to do is move the 1/2, so that's multiply by 2. Then we're going to move the mass by dividing by mass. And then I don't want to know the speed squared, I just want to know the speed. So take the square root of both sides. So we get the speed, the final speed of the car at point A, is the square root of 2 times the kinetic energy divided by the mass. Plug the numbers in. We add an EKF of 107,800 joules by using the law of conservation of energy, and a mass of 110 kilograms. Plug that in, and you get 44 meters per second. It's a good 92 miles an hour, which is a realistic speed for a 100-meter tall roller coaster. That's a little bit taller than the Millennium Force at Cedar Point, which goes about, I think, 90 miles an hour down the first hill. So this is actually a reasonable kind of thing you would get on a 100-meter tall roller coaster. So there's part A. Part B. Now I want to know what the speed of the roller coaster car is at point B. That's the top of the next hill, which if you look back at the diagram is 25 meters off the ground. Now before we even do this problem, let's just try to think of how we think this answer would be compared to the previous answer, where we were going 44 meters per second at ground level. Since we're higher up, hopefully you can see that our answer here should be less than 44 meters per second, right? Because some of the energy is going to be stored as EG. You're going to slow down basically as you go back up the hill. Now, we need to be a little specific about this one because there's a couple different ways we could approach the problem. And one of the choices we have to make is where is the initial? Where are we going to start everything at? We could do two places. We could do point A, but if we do point A, we have to use the answer we just found. So it might be easier to just use the top of the original hill. Now, since we're using only conservative forces here, no friction, that's one of the wonderful things about using only conservative forces. They are path independent, and therefore we can really start anywhere we want, and as long as we know where we start and where we end, everything will work out the same. So our final will be at B. Now the next choice we have to make is where is the zero of EG? In the previous part we said, well, let's make the ground zero, and we could do that here as well. In that case, there would be some final gravitational potential energy because you'd be 25 meters above the ground. However, we also could do this problem, and this will be a more clever, perhaps less math way of doing the problem. Why don't we just say, let's put zero height at B? That's going to cause us to make a little conceptual change later on when we plug numbers in. But the advantage of doing this is that if we put our y equals 0 meters at B, there'll be no EG left at B. So initially, no EK because it's at rest, no EE, no springs or rubber bands or anything, so it's all EG. I'm going to call that 4 boxes again. And like before, we now can actually calculate how much that will be by using the gravitational potential energy math model, mass times gravitational field strength times initial height. Well, our mass is still 110 kilograms. Assuming we're on the Earth, our gravitational field strength is 9.8 newtons per kilogram. And here's where we have to be careful. What will our initial height be? Well, here's where we have to consider what we're calling zero height. We're calling B zero height. So when you're at the top of the first hill, you're not 100 meters above that. You're only 75 meters above that. So that's the little conceptual piece you have to do if you're going to use this method. That means we only have 80,850 joules of EG initially. Put that up there on the initial table. Our energy flow diagram will look as before. There's our system boundary. There's what's in the system, the cart, the track, the earth, right? There's no energy flowing in or out, no work being done because it's still an isolated system. And so that means we have 80,850 joules in our final bar graph. No E-dis, no friction, no EE because there's no springs or anything. And here's again the special thing we did by choosing 0 to be at the top of B, the top of this second hill. There's no EG there either, which means all of the 80,850 joules is stored as EK. And exactly the same steps as before, once we know the EK, we can then solve for the final speed. Multiply by 2, divide by m, take a square root, plug the numbers in, and our answer is 38 meters per second. So as we predicted, it's lower. Okay, it's lower than it was before. One thing, you don't have to write all these steps. If you're good at algebra, you probably could skip from here to maybe here, right, and skip these two. But if you need to, write out as many steps as you want. Right? More steps is never a bad thing, especially if it helps you get the algebra correct. So there's our first example of quantitative energy bar graphs. I hope you enjoy the next worksheet.